Hi everybody, my name is Peter Grasso. I'm head of clinical support for the business unit Vibrant, and today I have the pleasure to give you some information about the Vibrant sound bridge and bone bridge fitting. We are going through the audio processors, the different generations. We are going through the fitting step by step, and at the end of the presentation we are also going to talk about outcomes with the middle ear implant Vibrant sound bridge and bone conduction implant bone bridge. So since 2001 we have different generations of audio processors. In 2001 we have been working with the AP404, and then in 2009 the Amadee has been born, which is a high-tech audio processor, and many patients are already using it. In 2014 we won the Red Dot Award for our audio processors, and in 2015 the last audio processor, the newest audio processor has been launched, which is the Samba, and we have the CE mark for it, of course. All the audio processors are backward compatible. That means that also the first patient who has been implanted in 1996 with a Vibrant sound bridge has the opportunity to use the last technology, and in fact the first patient is using a Samba right now. I have some good news at the beginning. I would like to tell you that the fitting procedure for all the audio processors, the Amadee and the Samba, but also the older generations, is very, very similar. The procedure itself is nearly the same. And this is true not only for the different implants we have, so the bone bridge and the Vibrant sound bridge. The fitting procedure does not change, but it's also the same independently where the FMT, for example, has been positioned surgically, or where the bone bridge has been implanted, if it's a sinodural angle or retrosigmoidal or in the middle fossa. The procedure itself, the fitting procedure, is always the same. So let's dive into the technical aspects of the audio processor. Let's start with the Amadee. The Amadee features 16 bands. It's a digital audio processor, of course. 8 compression channels, and there is a chance for the patient to choose between 3 different programs just by clicking at the button we see here. The Amadee also integrates directional microphones and some algorithms which enables to focus on speech and eliminate the background noise, which is annoying, of course, and may impede speech comprehension. There's only one battery needed. This is the only source of energy for the whole system, and it's a 675 zinc air battery, which is normally used by the patient, and allows the patient also to use the audio processor for more than a week in general. The frequency band we can address with the Amadee, this is a very important point. It goes from 250, so from very low frequencies, up to 8 kHz. And this is important, especially when it comes to speech comprehension in noise, where the high frequencies are so important to enable patients to understand speech better, even in not ideal environment. The Samba audio processor features many algorithms in addition to what we have seen for the Amadee, but it's also nice that there are so many different colors and designs the patient can choose. There are up to 5 programs, and of course a remote control which enables patients to switch between them. There is a nice algorithm which eliminates feedback and noise, so noise reduction is very advanced with the Samba. The Samba is constantly analyzing the environmental sounds, classifying them, and then switching to different algorithms in order to find the best settings in function of the different environmental sounds. There is also the possibility of wireless connectivity, a directional microphone, of course, and what the Samba also does is to simulate the pinna. So we know that the pinna is like a filter for the sound, focuses the attention towards the sound coming from the front, And the samba has the opportunity, has the chance to do the same. So there is a filter implemented which is very, very similar to the one which simulates the pinna. There is also an automatic microphone setting, and we will have a look into that, and I will tell you more about it. There is the possibility to track speech and to give the maximum attention to the sound source, reducing the background noise. And the samba also features self-learning algorithms. So now we are ready to see the patient, and we would like to be prepared to see the patient. What we normally do is to look into audiograms, into settings, and we have a very clinical approach to fitting. We would like to have at least the audiogram and the speech in front of us in an unaided condition. We are looking at the equipment we need. There is a slight difference between what we need for the Amadé and the samba. Of course, we need a computer, we need an interface, which is the Hyperbox, and we do need software. And the software which is important to have is the CONIX 6.4 with a database which is called SimFit 6.1 for the Amadé, and the newer CONIX version 6.5.5 for the samba with SimFit database 7.0 in order to program this device. Of course, we need the cables and the battery pills, as well as the USB cable to connect the interface to the audio processor. Now, whenever we see a patient, or we're going to prepare ourselves to see patients, it's always important to have the audio processor adapter, which is called APA, to confirm that the audio processor is working fine. We always would like to check the skin, the condition of the skin over the implant side. We would like to make sure that it's not red, or there are no problems regarding the skin. And then, of course, we would like to make sure that the magnet strength is appropriate for that particular patient. We have different magnets, they have different strengths from 1 to 5, and make sure always, whenever you see a patient, that the magnet strength is appropriate so that the audio processor will not fall off and the pressure would not be too excessive for the patient. So, what are we going to do next? We're going to detect the audio processor with an automatic procedure. We go to the software and we click onto that symbol you see here, which enables us to detect the instrument, which is the audio processor, which is connected to the interface. And then the next thing we are going to do is to perform a vibrogram, and we will see in a minute what a vibrogram procedure is. We have the opportunity to perform an audiogram through the implant, and this is true for the vibrant sound bridge, for the middle ear implant, as well as for the bone bridge, for the bone conduction implant. So how does that work? We have the opportunity to produce pure tones directly with the implant. And these pure tones are calibrated in intensity and in frequency, and we are going to ask the patient when he hears the threshold. So we are going to perform an audiogram through the implant, but we are not only measuring thresholds, but we will see that there's a chance also to measure the uncomfortable level. So we start with the threshold first, and we really measure it from 500 Hz up to 4 kHz. And as the software just gives us the opportunity to measure this frequency range from 500 to 8 kHz, it's important to extrapolate the information, also the thresholds, towards the lower frequencies and towards the higher frequencies, like we can see here in the audiogram. And this is something done manually. These points are measured, while these ones are just extrapolated in the very low frequencies, 125 to 150, and then 8 kHz. Very good. As soon as this has been done, we explain what UCL values are to the patient. So these are the intensities which are uncomfortable for the patient. So we are talking about very loud sounds, and also here we are looking at 500 Hz, 1 kHz, 2 kHz, and 4 kHz, and we do get these values, which indicates the whole dynamic range. So what is the dynamic range? The dynamic range is nothing else than the difference between the UCL values, for example at 500 Hz, in this case is 85 dB, and the threshold, which in this case of this particular patient is 25 dB. So we are talking about 60 dB of dynamic range at 500 Hz, and we see that it's very similar for the other frequencies. So thanks to this information, we exactly know which intensities the patients can hear frequency by frequency. And this information can be fed into the software, and the software will then automatically calculate all the parameters and provide us with a very good starting point, basic fitting. So if you look at the interface, how can we measure these thresholds and the UCL values? We have a tab which is called vibrogram. You see here the frequency range from 500 to 6000 Hz, and the different intensities from 15 dB up to the very high intensity. So normally we just use this as an audiometer. We start with 1 kHz and we will find thresholds and UCL values in the usual way, like an audiometer is done. Okay, this information not only provides the dynamic range we have been talking about, but more than that. The fitting algorithm is taking into account thresholds and UCLs, feeding the software with all the parameters needed for basic fitting, but it also is useful to verify the integrity of the implant, because as soon as we know that the patient is hearing sounds through the implant, we know that the whole system is working. But in addition to that, we can also compare thresholds with the bone conduction level we see from the audiogram. And if the difference, frequency by frequency, between the threshold measured through the vibrogram and the bone conduction levels is not bigger than 25 dB approximately, then we know that the coupling is perfect. And this is true for the bone bridge as well as for the vibrant sound bridge. So we have also some information about the surgery and the coupling of the FMT to a vibratory structure of the middle ear, or the FMT and the skull, the FMT of the bone for the bone bridge and the skull of the patient. In addition to that, we will see that in a minute, the vibrogram also provides us data which is useful to choose the appropriate type of AP, of audio processor. Very good. In reference of what we said about the coupling quality, I would like to mention one paper, which is Alexander Müller et al., titled "The Influence of the Floating Mass Transducer Coupling Efficiency for Active Middle Ear Implants on Speech Recognition." This is a very nice paper showing that if the difference between the threshold and the vibrogram is not bigger than 30 dB, 25 dB, then we may achieve a very, very good result with the vibrant sound bridge. The same is true also for the bone bridge, but normally it's very rare to see any coupling issue with the bone bridge as it's fixed to the skull. Okay, so as soon as the vibrogram thresholds are less than 30 dB, then it is advisable to use an audio processor, a low version of the audio processor. If the values of the vibrogram are higher than 30 dB, then a high should be used. This is a nice rule in order to give us the possibility to choose the most appropriate audio processor for the patient. Now let's go into the fitting step by step. And I would like to go through the most important concepts with you in order to provide you with all information to have a very good basic fitting. Then of course always fine-tuning is possible, but as soon as you have a very good basic fitting, I think this is the goal is reached. So what we said before, for example, for the Amade, for the Samba, we need a Connex 6.5.5 installed in our computer. We also need the SimFit 7.0 installed. We need the USB cable connected to the Hyperbox, to our interface. We need the appropriate programming cables. with a battery pill, and of course, in this case, a Samba. Then we launch the software. And here we have it. That's the interface of the software. And you can see that there is a button over here which allows us to get the test settings. And we would need to choose the vibrogram settings at the beginning in order to perform the vibrogram. As soon as this is done, we can choose the tab vibrogram, as you can see here in the software, and then we are ready to measure the vibrogram. Here again we see the interface which allows us to measure thresholds and UCL values, and we generally start with 1 kHz at an intensity close to the bone conduction levels of the patient. Here we see it even bigger. And then, as soon as we get the whole vibrogram thresholds from 500 to 4 kHz, we choose the AC symbol, so air conduction symbol. This is very important for the vibrogram. We always have to use the symbols. We have to feed the software with this information. We are inserting the measured value. We are extrapolating the frequencies, the thresholds for the lower frequencies and the higher frequencies. And if you also have measured the UCL values, you can feed this information to the software as well. As soon as that is done, we can just start the first fit procedure by clicking onto this icon over here. This window will appear. We have the chance to insert the serial number, which is not mandatory, and we would like to start a new fitting. As soon as this is done, we go to OK, and we choose whether the patient would like to have a remote control, a mini-tech, an accessory, which is available. Then we are ready to the first fit procedure. We choose the acclimatization level, which is very well known for hearing aids, and basically what the acclimatization level is doing is to increase the gain and the compression in accordance to the experience the patient has with hearing aids. So if there's no experience at all available of the patient, then we can start with an acclimatization level number 1. If the patient already has used hearing aids before, then we can choose either 2 or 3. If there's a lot of experience with amplification, then of course also 4 might be an option. Generally, we could recommend to use the setting 3 for all patients, also those who have not so much experience yet with amplification. Then you might choose the fitting formula you like the most, DSLIO or the NAL2. This is really up to you which fitting formula you can use. We generally recommend the DSLIO, and as we have a lot of experience with that, and so we normally just choose the acclimatization level 3 as a default and the fitting formula DSLIO as a default as well. Then for the remote control, we have the chance to choose the control range, and also here the default would be 8 dB, so that the patient has the chance to increase volume and decrease volume, but not more than that, not more than 8 dB. And this is like a safety feature which is useful to integrate into our programming. Then you have the opportunity to choose the number of programs. I personally like to have 1 program for every situation, but this is also up to you. You can choose up to 5 different programs with the Samba or reduce it to 3. Then we can apply the first fitting. That means that the software now has the vibrogram information, threshold and UCL values, has the information about the acclimatization level and the fitting formula, and is ready now to provide us with a basic fitting. We can then close this window, and automatically you will be led to this window where we see the following. We have on the x-axis, we have the frequencies from 120 Hz up to the very high frequencies, 8 kHz, and then we have the intensities here in dB. What the red curve is showing is the maximum output of the audio processor. And this is different if you're talking about an Amadé or a Samba. It's also different if you're talking about an Amadé which is fitted for middle ear implant or a bone conduction implant. So it really depends from which audio processor we have connected. Also, of course, it depends from the version, if it's a low or a high. But the nice thing is this is automatically read from the audio processor, stored in the audio processor, and then transferred to the software. Then what we see are some black curves and some red curves over here. Let's start to describe the red ones first. So the red ones show us the output in function of different input levels. For 40 dB, we will have this output over here. For 65 dB, the red curves here, this dotted line over here, shows us the output for higher intensities, for 65 dB, and then we also have the output for 90 dB. And these are the red curves. So what is the difference between the red curves and the black curves? Well, the red curves are the suggested amplification from the software, while the black ones is the actual fitting of the audio processor. If you perform a first fit, the audio processor is the red curves and the black curves are the same, so the audio processor is reflecting what the suggestions of the software is. As soon as you change some parameters in the audio processor, then of course there will be a difference between the red curves and the black curves. Very good. So this is the interface we have, it's a connex, and we can go through the basic tuning first, and then we switch over to the fine tuning we see over here. And if you want, you can also document whatever is you have done. So in the basic tuning, basically what can be done is to change the master gain, change the amplification for loud sounds, for speech, and for soft sounds, as well as the amplification of the own voice. There are some options also to modify the sound quality of the audio processor. If it's too sharp, then this can be the sharpness can be lowered, or if it's too muffled, also there. By clicking on this button over here, there is the possibility to improve the sound quality for the patient. This was the basic tuning. If we would like to go into the fine tuning, then we are looking into these tabs over here. We click on fine tunings, and then we see compression, sound management, microphone and Bluetooth settings, instrument settings, and vibrogram again. Let's start with the frequency shaping. We said that we had 16 frequency bands, and here that's the equalizer for the 16 frequency bands, so you can really increase or decrease the volume in a certain defined frequency band by just changing the controls over here, very low frequencies up to the very high frequencies. And what will change when you modify these values over here are, of course, the black curves. And like you can see it right now on the display, there is a difference between what the software is suggesting, which are here shown by the red lines, and what is actually programmed in the audio processor. We also have the opportunity to look into the compression values, the knee points, and the algorithms for each frequency bands, syllabic or dual, but these are very advanced parameters which normally are set by our vibrogram and the UCL values, and therefore are already pre-programmed by the software in a very in an excellent way, and there is normally no need to change those. Interesting is the sound management implemented in the Samba. And actually there are 4 algorithms I would like to mention. The speech and noise management, which can be set from minimum to max. And what the audio processor is doing is to enhance speech and reduce the noise. And this can be really done in a very individual way, from quite drastic change of the sound quality, of enhancing speech very much and reducing the noise very much, to a more linear way where the audio processor is just changing the sound quality slightly. Sound smoothing is also an interesting algorithm, which basically is eliminating some loud peaks in the sound. So if there is clapping of hands, for example, or the door closes in a noisy way, the sound processor is just eliminating these very intense sounds which may be disturbing for the patient. Interesting is also the wind noise reduction. This algorithm just monitors whether there is wind, and in case the sound of the wind is detected, this will be eliminated completely, reducing this disturbing noise to a minimum. Then, what is generally not very used in with the Amade or the Samba, with the middle ear implant, as well as with the bone conduction implant, bone bridge, is the feedback stopper, because generally we don't experience, or patients, they do not experience feedback with our devices. Of course, very interesting are the microphone settings, and this is very important that we check every time we fit the patient. There are different settings, for example the automatic and ambient sound, where the 2 microphones of the Samba are constantly monitoring the environment and then choosing the best configuration for the microphone, whether it is omnidirectional, whether it is directional setting, in a very automatic way. We are going to look into that in a minute in the next slides. Then we have the opportunity to track speech. So some patients, especially in a bar or a restaurant, they prefer to have this setting of the microphone, so that they are always focusing on who is speaking, who is talking, always focusing on speech, and so enhancing the signal to noise ratio in this particular environment. The directional adaptive microphone can also be set, and therefore what the patient is doing is to focus the attention on the speaker in front of him. So if the patient would like to appreciate music, the omnidirectional setting may be the most appropriate setting for the microphone in this particular situation. If you click on the instrument settings, there is the possibility to change the warning tones or the melody beeps as soon as, for example, the battery is low. But generally, we are not changing these instrument settings too much because the default values are already very good. I would like to spend some words about the microphone and Bluetooth settings and go in a little bit more into depth, as this is an important important settings which has to be done in an appropriate way. If you choose the automatic mode for the microphone, then the audio processor is constantly monitoring the ambient and detecting whether it's quiet, and in that case the transfer function of the microphone is set to simulate the pinna, like we see here in the picture. But if the audio processor is detecting noise, then the microphone setting may be set to the directional microphone, just focusing on the person who is in front of the patient. If music is detected, then the audio processor is automatically changing the setting to the omnidirectional microphone, enhancing the sound quality for music appreciation. But in case you would like to use the speech tracking as an option, then the audio processor is working in a different way. And the audio processor is just constantly monitoring where the speaker is positioned in relation to the head of the patient. So if the speaker is in front of the patient, the microphones are set in such a way to focus on the person in front. But if, for example, we are in a different situation, the patient is driving and there is somebody in the back seat talking, then the audio processor is just focusing on the backside of the patient. In a completely different situation where the patient is listening to a person talking from the side, then here again the audio processor is changing the setting of the microphone in order to improve the signal-to-noise ratio for that particular situation. For the adaptive directional microphone, there is again a new method, a new strategy implemented into the audio processor, and we can see here how the transfer functions of the microphone are. If there is noise, for example, from the back, then the audio processor is trying to eliminate that uncomfortable sound, which does not contain any information for the patient. If there's noise coming from the side, also here, what the audio processor is trying to do is to reduce this information. And this is also true if noise is detected from the side as well as from the back. And also there, for that situation, for that particular situation, the transfer function of the microphones are set in order to improve the signal and reduce these uncomfortable noises. For the omnidirectional setting, this is absolutely clear. There is no transfer function, no particular transfer function. Also, the pinna is not set. At the end of my presentation, I would like to show you a very useful tool, which is the fitting assistant. You may choose the fitting assistant by clicking on fitting, and then you will see here the fitting assistant in this tab. You click on it, and now you have the opportunity to improve the sound quality in different situations. For example, if you click on environmental sounds, and the lower frequencies are too loud, then you will find this particular situation in the fitting assistant, and the fitting assistant just provides you with some proposals on how to improve the settings. For example, decrease the gain for the low frequency is the first proposal, or decrease the maximum power output is the second proposal. And you find many hints and tips and tricks in the fitting assistant. So I really encourage you to use it and find solutions and the proposals there. The Samba audio processor also integrates an intelligent sound adapter. You can use it, you can have a look at it by clicking on this button over here. You find in the bar. And you will see some very useful information about the wearing time, about the program the patient has been using, in which sound environment the patient was immersed in, and of course all the microphone settings. You can find useful information about this one as well. The audio processor also integrates a self-learning algorithm. That means that if the patient is changing the volume in some particular situations, this will be just remembered by the audio processor, and after a week of consistent use, the fitting is automatically adapted, automatically improved, avoiding the patient to go back to the clinics many times. Okay, so what are the take-home messages? The vibrogram represents a very good base for the fitting. It gives a precise fitting. We have the chance to verify the dynamic range, frequency by frequency. We can feed this information to the software, and then we have already a very good base to improve then the fitting, to fine-tune the fitting then. The microphone settings allow advanced fitting for difficult listening environments. The fitting assistant should not be forgotten. It might be very useful in challenging cases and gives some very good hints on how to improve it. And then, of course, the intelligent sound adapter allows data logging, self-learning, and automatic fitting, and provides you with very useful information. As we said at the beginning, what I would like to present now are outcomes with the bone bridge as well as with the vibrant sound bridge. Let's start with the bone bridge first. And I'm presenting here 20 studies comprising more than 200 patients, and what we see here in the graph are many publications from Zheng et al. In 2013, and all different bars here represent different publications. And what we can see, and what is very similar and common to all these publications, is that the functional gain is approximately 30 dB. The mean functional gain is 33 dB for most of the patients implanted with the bone bridge. The improvement in speech understanding is shown in this graph. What has been done is to present speech at 65 dB and to measure the word recognition score in the unaided as well as in the aided condition. And there was a mean improvement of 60% shown in these 12 studies presented here in that graph. Also here every graph presents a single study. What we see here is the unaided situation and the percentage of speech recognition in unaided situation as well as the one in the aided situation, and you can appreciate the improvement with the bone bridge. Regarding the outcomes with the vibrant sound bridge, I would like to mention the following studies. There are studies which looked into mixed hearing loss and studies which look into the conductive hearing loss. And there are 44 studies I'm going to present you right now with more than 700 patients. And the mean functional gain for the mixed hearing loss group was of 37 dB, with a standard deviation of 9.1 decibels. And for the conductive hearing loss, the mean improvement of the functional gain was of 38 dB with a standard deviation of 10 dB. Regarding the speech comprehension in quiet 65 dB at SPL, also here we can appreciate that in the group of mixed hearing loss patients, the speech gain was of 55%, and we are looking at 483 patients and 35 studies, while the improvement in percent of the speech for the conductive hearing loss was of 74% with a standard deviation of 18%. 16 studies, 146 patients. There, as we have so much experience already, the first patient has been implanted in 1996. There are systematic reviews out there as well as long-term studies. And I would like to mention the one of Ernst et al., which was published in 2015. It's a very interesting paper, reassuming many other papers and showing the safety and efficacy of the vibrant sound bridge. Like we said before, long-term results in mixed and conductive hearing loss, there are many patients describing those. Boeheim, for example, et al. In 2012, Coletti, Mandala in 2013 looked into 40 adults and 10 children and a follow-up of 60 months. Very interesting is one paper which has been published last year, which is the round window application of an active middle ear implant in comparison with hearing aids, and this is a Japanese paper by Iwasaki et al. And I would like to give you some information about that because there is a direct comparison to the hearing aids. If you look at this speech comprehension with the vibrant sound bridge, patients affected by mixed hearing loss reach more than 80% on average with the vibrant sound bridge, and this is a 20% improvement in comparison to the best technology hearing aids available on the market is at 50 dB. At 50 dB. As well, we see that result also in noise, and here there was an improvement of approximately 3.7 dB of the vibrant sound bridge in comparison with hearing aids whenever it comes to mixed hearing loss patients. And this is very important information. As a conclusion, I would like to say that we have a lot of experience right now. The fitting procedure is very standardized. It's independent from which implant use, whether it's the bone bridge or the vibrant sound bridge, and how the FMT, the bone conduction FMT or the FMT of the vibrant sound bridge has been surgically fixed on a vibratory structure. Both the vibrogram thresholds as well as the UCL values are considered to calculate the target curves automatically. This is done by the software, and which provides then a very good basis for a fitting, as well as quality control of the surgery, like we said, as well as an integrity check of the implant. So thank you very much for your attention. This concludes my presentation.